Another important thing to talk about with continuity is how does the composition of two different functions affect continuity? Well, as I state here in this remark, it can be shown, using a very careful epsilon delta proof, that if a function f is a continuous function of two variables, and g is a continuous function of a single variable, then it is the case that you could do this sort of a composition. I could imagine saying, go to a function in like Calc 1, say a function like this, and in place of that variable of x, plug in an entirely new function that has two variables, maybe say a function like x plus y. And if I combine those together by plugging the red stuff into the blue, I can create a function like this, where I say everywhere there used to be an x, plug in the red stuff. And I've now created a function with two variables. So again, if it was the case that the red stuff is a continuous function and the blue stuff is a continuous function, then the result is also a continuous function. So this is really great because this will help us when we're dealing with calculating certain sorts of limits. So take a look here at like example 7. Here I'm not going to do any limit, but I do want to try to argue again whether or not this function is going to be continuous and where it is continuous. So note the following. What we kind of have here is an outer function g. I'm going to call it g of t as opposed to g of x, just to not have extra variables floating around. But notice here that this outer function would be something like the arctangent of t. That's the function that it looks like some xy formula has been plugged into. And this function here, we might recall from Calc 1, is continuous for all real numbers. There's no time when the arctan function ever becomes undefined. You might recall the arctan function looks something like this. It just happens to have horizontal asymptotes at negative pi over 2 and positive pi over 2. A very great function to know. We can also, though, see here that I have a function f of xy, which looks like y divided by x. And this is a rational function, so it should be continuous as long as the denominator is not 0. So it's continuous everywhere except where the denominator is 0. So I should be able to say that this is continuous except along the line where x is equal to 0. So remember, any point where x is a 0 is going to be a problem. So here, if I'm looking at the domain of this function, I get a bunch of bad points along the line, oops, sorry, not that line, but along the line where x is always equal to 0. Every point on there is bad and would not allow an output to be created. Okay. Notice here, I'm sketching two different pictures. This here is the picture of the arctan. This is not the picture of the function. This is just a picture for the domain of that function. All right, so once I have these kind of two ideas down, I know the domain of the first one, and I know the kind of now the domain of the next one, and where those things are going to be continuous, then I can definitely say that my function h of x comma y is going to be continuous, well, kind of everywhere where both of those things are continuous, which apparently would be everywhere except the line x equals 0. So I can use these two individual functions continuity properties and figure out kind of where they overlap to create a continuity for the larger function. In the red and blue example that I have over here, you can actually see that my resulting function over here would be continuous everywhere because my first function in blue is a nice continuous polynomial from Calc 1, and the second one is a continuous polynomial from our multivariable functions. And so when I combine them in this composition, I end up with a continuous function.